I apologize that I cannot be there right now. It's 2 in the morning and my son is throwing up, and so I am recording this video for you. All right, so again, today your assignment is to continue working on the Friction Virtual Lab. I'm going to go through a couple things here with you to make sure that there are no misunderstandings and that you know what to do. Okay, so the first thing that we are looking at here is it says to click on the net force, and we're going to go ahead and apply 200 newtons of force to the left rope and 150 newtons to the right rope, and look at the magnitude and direction of the resultant force. So if we are to do that, that is going to be nice 100 newtons of force there. We can add 2 more little guys to make it 200 newtons there. And we can do 150 newtons there. So the sum of forces is 50 newtons. It is to the left. And that is what they are asking at this point. Apply the 200 Newton force to the left rope, 150. What is the magnitude and direction of the resultant force? That is 50 newtons to the left. The next thing says click on go. What direction is the car moving? We should see it moves to the left. And observe the speedometer as the car moves, what's happening with the velocity, and explain the cause of the velocity's behavior. As we look at this, the speed is going on up. It is moving to the left with increasing velocity. And so we should see that because we have a net force, we have an acceleration in that direction, which is Newton's second law. Remember, this whole idea of what we're talking about is Newton's first, second, and third laws. We're going to get to third law later this week. So the second law is what applies here. If we look, we see that there is a change in velocity. It's accelerating. And to explain the cause of the velocity's behavior, we would use Newton's second law. If we apply a force, a mass will accelerate. So then we go to part 2, which is motion. If we hit up motion, the idea here is it says click on the masses, values, masses, speed, all those fun things. And we're going to push the skateboard and box with a force of 500 newtons and observe the behavior of the velocity once skateboard is released. So if we go ahead and apply just the full 500 newtons and release it, then we will see that it will maintain constant speed, right? Nothing is happening to it here. It is not slowing down. It is not speeding up. It is maintaining constant speed in this case. And so how do we explain that behavior? Well, this behavior is dictated by the idea that there is no friction. And if there is no friction, we should know from Newton's first law, explaining the reasons for such behavior. Newton's first law says that an object in motion will stay in motion unless acted upon by an outside force. And so in this case, it's jamming at about 6.1 meters per second. And it doesn't really matter what speed, like, so if you did this fully and you just like, totally all the way up, well, he can't go faster than that. So it just maintains 40 meters per second. That's fine as well. But either way, you recognize that it always stays at constant speed. And that is Newton's first law that explains why that does that. So then we're going to go into part 3, which is friction. I'm going to change this guy to friction here. And it says, keep the knob that regulates friction center of the scale. Start to push the box, increasing the force applied on the box slowly. There's a force that is opposite to the force you are applying. What is the name of the force opposing the motion? So if we start applying a force here, we're supposed to do this slowly, but either way, I'm going to do it with this setup here. We see that we're applying a force in this direction. What is the force that is opposing motion? That is the frictional force, which we should be used to understanding is going to oppose our motion. So we're going to go very slowly, and it says once the box starts moving, the magnitude of resultant force increases instantaneously. How do you explain that? So let's go and see what happens here. Excuse me. All right, so if we go on up slowly, 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 when we actually reach 126 newtons, all of a sudden we are having 32 newtons of force pushing on this box. It doesn't all of a sudden go from 125. Let me reset this actually where we have all of our fun stuff here. Okay, so if we go to 125 again, at 125 newtons, we have 0 forces as our net force. But all of a sudden, with 126, we end up with 32 newtons of force. And so we have to ask the question of why is that? And to answer that question, I want to go back to this picture from the lecture. If you remember, when we are applying a force against static friction will build and build and build against us until this magic point where it can no longer hold, at which point the force of friction becomes kinetic friction, which is always less than the maximum static friction. Okay, so this little area right here, the difference on this graph from the top point here to where the kinetic friction takes over, on this lab, that would be 32 newtons, that difference in force. Okay, because it was able to withstand, basically, it was able to withstand 125 newtons, right? But now that it's moving, it's only able to put out 94 newtons of kinetic friction. So we went from being able to put out 125 newtons of static friction, but then we broke it with 126 newtons of force, and then it got it moving. And once it was moving, it was only able to push back with 94 newtons of force. And so that is what we are looking at when we try to explain, once the box starts moving, the magnitude of the resultant force increases instantaneously. How do you explain that? That is going to be the difference between static and kinetic friction, right? That little guy right there. Okay, so as we go through, what we want to do is we just found, basically, that if we only have the box, which is 50 kilograms, our weight is always going to be our mass times gravity. So our weight here is going to be 50 times 9.8 meters per second squared, right? 50 kilograms times 9.8 meters per second squared, which is going to be 490 newtons. Now, because of the fact that the box is not sinking through the surface here, we know we have 490 newtons down. We have 490 newtons back up. That is our normal force. The force of static friction that we found, that force that it could take up until it broke, was 125 newtons. We will find that if we do this with a total weight of 90 kilograms, which we get by adding the little girl on there, we can go up to, again, I'm going to bring this back down, 225 newtons. Press play. Oops, I've got this, we don't want him moving anymore. All right, so in this case, let's bring all these guys back. We can go up to 225 newtons. And still not break static friction. Static friction is able to fight us and say, no, you're not moving this box. And then we get just one more Newton. And all of a sudden we've got 57 total Newtons of force here. We've broken static friction. We have a leftover. So in this case, our overall difference there would be 57. Okay, but what we want to be doing is we would just want to write that 225. So we're going to do that with all of these masses with a total of 130, with a total of 150, and a total of 180. Okay, so we can do this any way that we want to. If we want 130, well, that's 50 plus 80, right? If we want 150, that's going to be trash can and box. Oh, that's lovely. And if we want 100 and, I'm sorry, okay. Sorry, I've got vomiting going on in the other room over there. We have 150 We have 130. Sorry, we have we have 90, 130, 150, and if we are looking to get 180, we can actually take the box over here if we want and just put guy and the trash can if we want to do that, and apply all of our massive force. All right, so you get the idea there. Okay, so once we're done with that, what we're going to be doing is we understand, like on our first friction lab, we had the ratio shown to us of the height over the. Sorry, my wife is taking care of this, but I'm going to close the door so we don't hear any more vomiting over there. We saw that the ratio of height to horizontal distance gave us our coefficient of static friction. The reason that that worked is because we were actually, without knowing it, we were calculating the ratio of the force of static friction by divided by the force of the normal force. So we were actually doing this calculation by doing this with height. Same basic difference. So what we're doing here is we're going to take this number and divide it by that number here. So 125 divided by 490 in the first case, and this number it's 225 divided by 882 in the second case. So that is, we're going to continue that on with 130, 150, 180. And then you're going to say, how do they compare? How do all those numbers compare? So the last thing that we need to do here is we are trying to figure out kinetic friction. And so we already kind of looked at this and saw this with the first time we did this. We saw that if we break this with the 126, then all of a sudden it slides. What we want to find now is actually we want to find out, sorry, not that whole fun thing. We want to find out what is the minimum amount of force required just to keep this going at constant speed. So we have to back this all the way off. Back it all the way off. We want to get to that sum of forces being 0, right? And we should pretty much, we honestly don't even really need to do this because we can actually just look and see what the frictional force is. Frictional force is 94 newtons. And so to get our sum of forces equal to 0, we have to just have an applied force of 94 newtons. And once we do that, we will see that we just continue on at constant speed. Okay, so our force of kinetic friction is 94 newtons. Okay, and that's what we have written here. And we're going to do that with the 90, the 130, the 150, the 180. And we are then going to calculate our coefficient of kinetic friction by, again, dividing 94 by 490, 169 by 882, et cetera, and then seeing how these numbers compare. So hopefully this helps you with today's lab, where you can finish it by the end of today. Please email me if you have any problems with this. All right, have a good day. Happy Wednesday, guys. Take care.